Hi, welcome to my channel. Today I am going to solve one problem. So let's first read the problem description. Here's the problem description. We are given a list of words and a pattern, and we need to find all the words that match the pattern. A pattern can contain lowercase letters and a dot character, where the dot character can match any letter. So here are some examples. So we are given a list of words: dog, cat, cock, and Java, and a pattern .og. Then we should return cock and dog because those are only two words which match our pattern. In the second example, we have a pattern with all the dots, and the output should contain all three-letter words because our pattern contains 3 dot characters. In the last example, the pattern is all letters, and the output should contain that word if it also exists in the input. Of course, this is not the usual problem you would face on your day-to-day software development job, but you may be asked similar questions when you do job interviews. To solve this problem, there are several options. The very first one, you can try to iterate over the list of words and try to match each word with the pattern. The second one would be to store the words inside the hash map, where the key for the hash map is the length of the word, and given the pattern you can fetch all the words which have the same length as the pattern and try to match a pattern on a subset of the words. But today I'm going to solve this problem using a Trie data structure. Trie is also like a tree-like data structure. Unlike, for example, binary search tree, it doesn't have 2 or 3 child nodes. Instead, it has as many as child nodes as a number of letters in our alphabet. And for this problem, we assume that our alphabet is all lowercase English letters. So each node in a Trie would have child nodes of the size 26. Of course, you can read more about the Trie data structure. There are really good resources you can look up on the internet. I am also going to share some links in a video description. So let's get into the implementation. First, I'm going to create a node class, and it's going to have two attributes. And let's initialize it. Initially isWord is false. The children. I just mentioned that each node can have 26 child nodes. So this array, children array, is the number of child nodes, but for now I'm going to initialize it as of size 128 because it's just a convenience. Given a character, I can directly index into this array to obtain a child node corresponding to that character. So I don't have to shift it between 0 and 26. But you can change it. It is very easy. And what's the isWord? IsWord is a flag to indicate if the word was indeed added to our data structure, and we are going to see how we can use it when looking up a word or when searching for a pattern in Trie. And I'm going to also create a root node. And let's initialize it when we initialize a Trie. And the next method we can implement is somehow we should be able to add words into our data structure. So let's add a method for that. And the idea is we are going to walk trie starting from a root, and each character inside the word is going to tell us which child node we should move next. For that, I'm going to create a temporary node here and iterate over the letters of the word. Okay, now I need to move, given a character, I need to move child node corresponding to that character. But first I am going to check if it was initialized before, otherwise we would get a null pointer exception. If it wasn't initialized, we can just initialize it here and move my node to that child node. Okay, so at the end of this loop, we are at the node which corresponds to the last character of the word, and now we need to set its flag to true, because indeed a word was inserted into a trie and it ends at this node. Let's add also another convenience method so that we are able to add a list of words. And I'm going to use var args for that. Okay, now we are able to add words into our trie data structure. So now let's implement the search method. It's going to return list of strings. The parameter is going to be a pattern. And to do the search, I'm going to implement it as a recursive function. And for that, I'm going to also use a helper method, which takes a root, a pattern, a position in a pattern, which corresponds to which letter inside the pattern we are now exploring, and also a list of characters as a prefix, and the result, which is going to store all the words we matched with the pattern. And let's add them all. The prefix is going to store all the characters which correspond to the path from the root to a current node we are now exploring with our recursive function. So we are going to add a character to this list and also remove a character once we finish our exploration of any particular child node. So let's resolve this I want list from util, and also array list. And yeah, here I'm going to also return a result. Let's also implement our helper method. Node pattern position, and we have character prefix, and also the list of strings we found that match the pattern. Okay, so with all the recursive functions, the very first thing is we should have a termination condition, and one of the termination conditions here can be if node is null, we can just return, and another one is if we are already outside of the pattern, which means that we already explored all the letters of it, then we can return. And now I need to let's get the letter at this position. It's going to be so it should be pattern, sorry. At this point we have a character from a pattern at a given position. So that character can be a dot. Then we should do something. It can also be a specific character. So in that case, I can directly move to the child node of the current node, which corresponds to that character. So I can continue my search using char at position and also a pattern. I'm going to increase the position by 1 because we already just now a char at position corresponds to the character at position, so I need to increase it by 1 when going into the next call of the recursive function. And similarly add all the other parameters. But now here I want to update my state with character at position, and once I return from this recursive function, I need to again update my state, which means I need to remove the character I added before calling the function, and that is going to be the last one in this prefix list. Prefix array list. So it's going to be size, the last character we are going to remove. Okay, but what do we do with the dot? So as we discussed in the problem description, that dot can match any character in our alphabet. So here we can just iterate over our alphabet. And substitute it for the dot. So I'm going to call the same, but instead of character at position, I'm going to call it with the substituted character. You may notice that there may be no child node which corresponds to that character, and that's okay, because in the function we check that if it is null, which means there is no child, then we are going to return early from the function. Okay, I think that's it, but as you can see, we don't update our result at all. So when we can do that, we can do it here. At this position, we know that we consumed all the letters inside the pattern, and we are at the last letter. So we can check that if the current node has a flag updated to true, which means we added a word, so there is a word which was added before, then we can construct a string using the all the characters in our prefix list and add it to our result. So for that, I'm going to check if the word was added before, and I'm going to use string builder to create a string from the list of characters in prefix. And add it to our result. I need to convert it to string. Okay. One thing I'm going to do is here I have a variable as a prefix, but I don't use it at all. So I can just put here array list itself. Okay, now it looks okay. We can test this method, and I have a test suite prepared. So let's first create a try itself. And let's add some words to it. So we can use our function. So in the example we had cat, dog, cock, and Java. And let's do this. So we are going to search .og, and that should return a list, and we can check that the list contains a cock and dog. Let's run this test. As you can see, the test passed, but let's add some more. Then another example was all the dots, and it should return cock, dog, and cat. But this is going to fail because we return a list of words in lexicographical sorted order. Because if you remember, when we have a dot character, we start the search starting from the A and starting from the B. So all the words we are going to find first will be starting from the A, and the list is going to be sorted in lexicographical order. So we can change this to that, because contains also checks the order of the list. And the last example was Java. And here it's a single word with a Java, which also exists in our input list. Let's run the test again. Okay, so test passed, and I think that's it for today. Thanks for watching, and